Oh, hey, Anna.
Hey, Gary. What you staring at?
Well, I was looking at this bridge. It's a brand new bridge. It's really something, isn't it?
Yeah, it's quite a wonder of modern engineering.
It is. That's civil engineering, like roads and bridges. Hey, I got an idea. SciEngiMathePloration should do a show on civil engineering.
That's a great idea, Gary.
Yeah, we could look at roads and bridges and how they're built and things like that. All right, but wait, hold this.
Okay.
For civil engineering, we'll need our hard hats.
All right.
Here we go. SciEngiMathePloration takes on civil engineering, roads and bridges.
Let's go.
Hi, we're talking about civil engineering, and to take you right on the scene, we've come out to a road construction site. I'm here with Craig Bryson, who's the Public Information Officer for the Road Commission for Oakland County. Craig, thanks for having us out.
Thank you.
This is quite a project we got going on behind us. Tell me a little bit about it.
Well, this is about an $11 million project. We're widening a 2-lane road to 5 lanes. We're building a new bridge over I-75, have a significant impact on traffic flow in the area. It'll be a much safer road. It's meeting all the goals of the Road Commission, reducing congestion, improving safety, improving traffic flow, serving the residents of the county.
The Road Commission is a busy group. They got things going on all summer long.
We do. This is a major construction season for us. We've got about nearly $30 million worth of projects going this summer, so it's a big year for us.
Great, and our host on this particular site, this is Tom Buss. Tom, you're a civil engineer, is that right?
Yes, I am.
Well, tell me a little bit about civil engineering. How did you get interested in that? What kind of training do you have to have?
That is interesting. I love civil engineering. It's a real people-serving profession. In fact, that's its motto. I was in college, didn't really know what I wanted to do, ended up on a survey crew for a summer job, and every place we went by, it seemed like the crew chief said, oh, I helped lay that out, or we designed that, or whatever the case was. And it was really, really fascinating and very satisfying to know that you're part of something bigger that actually gets built, is there. You can step back and say, I had something to do with that.
All right, so civil engineers, that's all about roads and bridges and utilities, things like that?
Right, roads, bridges, dams, airports, wastewater treatment plant, water distribution, just about everything that serves the public infrastructure.
So this is a road and bridge building project here today. What kind of things are we going to see?
Well, today what we're going to see is we're going to see them actually building part of the road and part of the bridge. We're replacing a 2-lane road here with a 5-lane concrete road. And what you're going to see today is the actual final part of that, the actual pavement itself.
All right, let's take a look at some of the stuff behind the scenes. So, Tom, what's the first step in building a road like this?
Well, the first step, of course, is just what's there and what do we want to build. In this case, as I mentioned, we had a capacity issue. We take into account what do we need to improve the capacity, and safety is always paramount with us. Then our survey crews go out, and they actually survey all the whole existing topography, it's called. And what that does is it gives us a plan view. A plan is nothing more than a drawing of what's out there. So when you see the actual pavement of the road, that's really just the top layer. There's all kinds of design that goes into it before you get to that point. The number one rule in building a road has got to be drainage. The water has to go someplace. If it sits on the road, 2 things are going to happen. You're going to have cars hydroplaning, slipping, losing their traction, causing crashes. And also that road is going to eventually seep down, undermine the road, and weaken it, and the road won't last nearly as long. Now the pavement section, as we'll see here in a minute, is actually multiple layers of materials working together. All pavements have a gravel base underneath or an aggregate base. In our case on this one, we've wrapped that aggregate base in a geotechnical fabric The geotechnical fabric keeps the aggregate base from separating and getting mixed in with the existing soils underneath. It provides strength for the pavement section up on top, and it also provides under drainage so that water that does sit or flow through the road or get under the road flows out and is carried away.
Great, and we can take a look at some of these things?
Exactly. It's exposed over here. I want to show you the cross-section that we're actually building.
Let's do it. Now, Tom, right here we're actually seeing some of the things you were talking about, the layers of the road. What are we looking at?
Excellent point. What we're standing on right now is the existing grade, or the subgrade as we call it. And you can see it's just a mixture of dirt and such, but this isn't too bad. Sometimes we have swamp and such that we have to get rid of and move out. This was good enough that we could use it. We cut down to where it's fairly strong and stable like this. We then use a heavy roller. Now this one actually vibrates and rolls. It packs that all down, so it'll consolidate it, give it a great strength. Next, we put on a layer of fabric on top of that. The black stuff behind me here is a geotechnical fabric, and that will act as a separator barrier between the old soil, which has a lot of fine aggregates in it, to the next course, which is a coarse graded aggregate. It's very large stone, very clean, not a lot of little fine sands and clays and such, and that promotes drainage underneath the pavement. On top of that, we're going to put another layer of fabric, and then on top of that next layer of fabric is a more mixed aggregate base. That second layer of fabric that I mentioned does the same thing the first one did. It separates the two different kinds of aggregates so they don't mix together, so they retain their strength. And then the top course of that aggregate will again be vibrated together. We'll put the concrete actually on top of that, so that the whole section is actually probably more in the neighborhood of 2-3 feet deep, rather than what you just see on the top is the concrete.
Tom, here we can really see these layers we were talking about. What's going on?
You're right, Gary. This is a great spot to see all three layers. We're going to see the aggregate course, the drainage course, which is the thick, heavy aggregate you see on the bottom here. You can see that that's large, 1-inch stone or so, very few fines in it. The fabric's on the bottom of that, another fabric on top of that, another layer of fabric on that. Then we have another 6-8 inches of aggregate. This is actually called 21 AA. And this has both large stones, small stones, and even some fine aggregates like that. This adds to the strength of the concrete, or actually the strength of the pavement section. And then finally, of course, at the top, you can see we've got a 10-inch concrete section. This is actually non-reinforced concrete, but you can see the dowel bars, the steel bars sticking out. That will span the joint between that and the new concrete. It just goes about 18 inches in each direction.
It's quite a sandwich, a double or triple decker sandwich by the time you get all those layers in there.
Yeah, this is a Big Mac here. This is a 3-layer.
All right, great. We also see some of the drainage hoses coming down the side here, and we're right in the middle of the project right here.
As a matter of fact, I'm glad you mentioned that. I mentioned how drainage is so paramount. The first course, the aggregate base, the coarse aggregate base, the large stone, as I mentioned, carries the drainage. That drainage will drop into these edge drains. That hose there has holes in the side of it, so it actually does take the water. It'll run it down to eventually, we'll put a catch basin here, and then that eventually goes to the larger storm sewer and eventually gets carried off to wherever the drainage goes, usually a drain or a stream.
Wow, this road stuff is pretty complicated. Let's go down the street and take a look at the bridge.
The bridge is even more complicated. It's really neat.
All right, great. Now, Tom, here we are at a site where the Road Commission is busy building a bridge, I guess. What did it take to get the project to this point?
Well, as we mentioned before, the bridges are probably the most interesting and dynamic part of civil engineering. They're the thing that people see and say, ooh, those are the greatest thing. The bridge itself started as we did the road. We start with what was existing there, including the utilities and et cetera. Look at the drainage. And most importantly, I mentioned the soils when we were talking about the road base. Soils are so important with the bridges because what they're doing, the bridge is spanning between 2 points, and it puts all that load on those few areas, as opposed to the road, which is basically on grade. And on the ends here, you can see that they build retaining walls. These walls are actually, they go back into the soils quite a ways, 30, 40 feet. And they actually then support this end of the bridge. In the center, there's a couple of piers. The poles that you see there are piers. They hold up a cap, which then holds up the road beams and the bridge itself, the beam or the bridge. And this is civil engineers doing their job. The public uses it every single day. But if you do it right, nobody really notices. The bridge doesn't fall down, the road doesn't fail, the sewer, the water comes to your house, the sewer flushes, whatever.
So all the pre-work and the planning and the engineering, that's the cake underneath the icing, and that's where most of the work is.
That's the part you don't see, and that's the fun part about being an engineer. They said it's a real people-serving profession. That's the part that nobody sees, but boy, once it's done, you can drive by this, and every day, whoever designed this is going to take their family down this road and say, I designed that bridge, I built that bridge, and that's what makes civil engineering so great.
Do you get to sign your name on one of the beams? Or?
I wish, but I can't take all the credit. I have a fantastic team that really did all the work.
Hey, we really learned a lot about civil engineering today and building roads and bridges. I'd like to thank my guests who helped make this all possible today. Craig Bryson, the Public Information Officer for the Road Commission for Oakland County, and Tom, the civil engineer right here on site. Thanks a lot.
Thank you very much. Appreciate it.
Thank you.
We're here today at the Road Commission for Oakland County Traffic Operations Center, a really exciting high-tech place. My guest today is Danielle Deneau. Danielle is a signal systems engineer and the Fast Track project manager. Did I get that right?
You did.
All right. How are you doing today?
I'm very well, thanks.
Well, this is a really exciting place to work. I see all sort of high-tech screens here and computers. What's going on here?
Well, this is where we house our signal system, which is called SCATS. It stands for Sydney Coordinated Adaptive Traffic System. It comes from Sydney, Australia. And the basis of the system is it adjusts the green time as cars are driving through the traffic signals to drive people safely and efficiently through the county.
Right. So here we are. We're at the Nerve Center, and you're controlling the traffic lights all over the county from here?
That's correct. We have the largest adaptive system in the country. We have about 650 intersections that run on this.
Wow. So you say an adaptive system. That means to me that things are changing or that you can make changes as you watch the traffic?
That's correct. As the cars drive through the traffic signal on the green, it's counting how many cars are going through it. Does it need more time? Does it need less time? So it'll change that based on the flow of traffic.
Wow. So somewhere there's a room full of people with counters and they're counting things up. They use abacuses, I presume? Or?
Nope. It's all done through a computer, through a PC.
So it's automated entirely. There's really isn't any human intervention. You're watching intersections and some kind of counting is going. How does a computer do that if there isn't a person involved?
There are people involved. We have engineers here that they need to set up the signals. Once they get connected to our SCAT system, we have to set up some parameters, some high levels of cycle length, some lows, the maximum green time, minimum green time, stuff like that. So we have to set all that up, and once it gets set up, then the computer takes over. And it adjusts at the time based on the traffic that's going through the signal.
So the counting, is that done through like weight sensors in the road, or are there cameras involved? How do they know what's going on out there?
It's done through two ways. The first is a loop that's embedded. It's cut into the pavement. We have contractors or our crews that go out there and cut them in the road. Or the majority of our system is autoscope cameras. We have about 2,000 of them. They're on the middle screen, and they show as vehicles drive through a zone that we've drawn on the screen through a computer. As cars drive through there, it sends a pulse that says, hey, I'm here. You can turn the signal green.
Oh, I see. So now this is an example of one of the cameras, I think, right here, isn't
Yes,
it?
it is.
And it is actually a video camera. It can see a picture, but I understand it doesn't really take video pictures necessarily.
No, it doesn't. It's purely just to look at the cars. It looks down at the stop bar, which is the big white line on the road. It looks down there, sees the car that's there, and sends the pulse back. There's none of the video. We don't see any of the video. Only at the intersection. You have to go out with a computer, plug in a monitor, and look at it. The only intersection that we can bring the video back from is one location. That's just for demonstrations.
I see. And behind us here, we do see a lot of these samples and things, and we'll take a look at those a little later on. Well, what's the effect of a system like this? It seems to me that you said, I think there's over 2,000 cameras out there, and that's a lot of technology. What's the impact of it?
Well, we don't have the funding to build our way out of the congestion on the roads. So we're using an adaptive system to try to get more out of it. If we can use the system to get more green time out of the traffic signal, that's a great thing. If we can reduce your delay, increase your safety, that's great.
That's good. Now, so what's the future of a system like this? I mean, it sounds like something that we're building and improving, and computers are advancing and autos are advancing. So what happens next?
Well, hopefully there's some technology coming called the vehicle infrastructure integration that will have traffic signals that can talk to cars. let them know when they're going to turn red so we can avoid collisions, avoid accidents, reduce congestion and delay.
Now,
that would be great.
Is there any chance I'm going to have a button in my car and when I push it the light turns green for me?
No.
Oh, darn it.
Not for you, Gary.
What are some of the other impacts? I understand that you do have statistics that show there has been a positive impact on traffic accidents or things like that.
Yeah, we're one of the safest counties in the world. We have a very low fatality rate. We reduce delay, reduce congestion, increase safety. That's what we do.
And that's what you do. Now, what's your training? How does one get to be a traffic systems engineer? What kind of training or schooling did you have?
Well, I went to Michigan State University. I graduated with a civil engineering degree, and there were basic traffic classes there that I took. And then I came to the Road Commission and got a lot of my knowledge hands-on. This system isn't taught in school. So when I came here, I learned a tremendous amount and progressed up through that, learning how to do signal timings and learning how to run scats and just adapting to the new technologies that we have.
Now, Danielle, this is one of the workstations here at the Control Center. What are we looking at here, and how does that control activities?
This is the traffic signal that's out at the corner at Pontiac Lake and County Center up here in Waterford. And what it shows is it's running adaptively, and it shows us the green time, the cycle length that the intersection is running, the amount of time that is to service all approaches, and it shows the vehicles as they're driving through the intersection. And one way to show that is the screen that's behind me. As cars drive through there, they place a call, and when the box goes green on that screen, it will go blue on my screen so that I know that there's a car there.
This is the controlling device that then guides them through the intersection depending on what lane they're in and whether they're going straight or turning.
That's correct. On the left side of the screen, it shows some stages, and that's the different phases that the intersection can run at this intersection.
So from this control panel, if you wanted to, could you turn all the lights red and make everybody wait?
No.
Now, I see on the left side of this screen there's actually some pie charts. What are those showing?
Those show the percentage of time that each direction got. The top pie chart shows what was running in the last cycle, and the one below it shows what's actually running at this moment.
So by looking at the two of those, you can get a feeling for how traffic is increasing or decreasing or the changes that are going on over time.
Correct.
Okay. Well, so what's the future or what's happening next in traffic? Are we going to see something new or different?
Well, I think there's just a lot of new technology out there. A lot of signal systems are evolving. This is an older technology, but it's changing every day. And there's a lot of technologies out there that want to get involved in signals and helping them run adaptively. So there's a lot of new stuff out there.
Great. Okay, great. Well, thanks for having us.
Thank you.
Hi, we're out here in Ann Arbor, Michigan, and an exciting new concept in parking lots and parking lot pavement. My guest here is Jason Schwarzenberger. Jason is with Soil and Materials Engineers. Did I get that right?
Yes.
Oh, that's good. That was the hard part. Jason, I understand you're a civil engineer.
Yes, I am.
What do civil engineers do? It sounds interesting.
Oh, design buildings, bridges, roads, transportation, basically everything that you see that's been built is somehow related to civil engineering, so.
All right, well, today's show is about roads and bridges, and if you got roads, you need parking lots, I guess, huh?
Correct. Everybody needs a place to park so they can go do their shopping or, whatever they need to do in town, so.
Now, this parking lot we're in right now, I understand this is a kind of a new concept, something special about it. What's going on here?
Well, what we did out here was we put a porous pavement in. Instead of a conventional asphalt pavement, we made it a porous system, so rainwater actually drains through the pavement and into the subgrade, so.
So this is a way of dealing with stormwater. I understand when you do have pavement, there's a lot of issues with water and getting it into the storm drains, and if it gets into the storm drains, it goes right into the watershed, right?
Exactly. With more and more buildings going up and more areas being developed, the strain on the existing storm sewer system is, obviously increasing. So what we've developed out here is a porous system where the water drains into the ground and doesn't go into the storm system, so.
All right, well, porous, and that's kind of a big word for it's got holes in it, right? I mean, the water just goes right through it.
Correct. Yes, correct.
Wow, I see. And now I understand this site that we're on, you had an advantage here is that there used to be a building here. There was a basement, so you started with a big hole in the ground.
Yeah, the city of Ann Arbor had an old YMCA building here, and they recently built a new one down the street. So it was an old building, and they tore it down, and they wanted to develop it into a new site, but in the meantime, they said, well, let's make it a parking lot so people can, we're right near downtown here, so just give people another way to get downtown. And when we did that, we looked at the site and we had basically a hole to fill up with the basement. So it was really conducive to putting in a porous pavement, because we were basically filling up from the ground, so we could put whatever we wanted to in there to help the groundwater filter, or the water from the rain filter through into the ground. So,
Right.
And this area of Ann Arbor has a lot of sand and gravel underneath, so that water just keeps going and drains down, probably 20, 30 feet. So.
All right, great. Well, I understand you brought some samples with us and some things we could look at, and maybe even an experiment we can try with this whole permeable pavement idea.
I want to show you the difference between the materials used for a regular asphalt that you'd see on a road or any typical parking lot, and then the materials that were used to make the porous system up, and how the two work and relate to each other. So
Great. Let's see what you brought.
okay, great.
All right, we're over here at the table. Hi there, Josh Parker, right?
That's correct.
And Josh, I understand you're also a civil engineer with SME?
That is correct.
You're going to help us out here today.
Yep.
All right, well, what do we got, fellas? Tell me what's going on here.
Well, first off, I want to show you what regular pavement looks like. Here is a core from a parking lot that we took, and you can see it's pretty solid, no voids, a nice solid system there.
Yeah, I can't imagine anything goes through that. It just runs off.
Correct. And before it gets compacted into this, you can see here, this is the material, the asphalt material. It's got sand and gravel and the asphalt cement in it.
Okay, so that's normal asphalt, the kind we see on most roads.
Correct. And what you'll also see is aggregate base put on, and it's crushed. This is crushed limestone here, so you have limestone, and it's crushed down, so you have some fines in there. So you really have a really well compacted base that doesn't allow you to really drain anything through. It's more for structural support, as instead of letting things drain through it.
Right, and I see that in this sample there's all different sizes. I mean, there's even sand or powder even in
It's
there.
going to range from anywhere from an inch in diameter down to little pieces of sand.
Very small pieces. Okay, and then by contrast, what else is here in front of us?
Well, here's the porous pavement that we took out and put down on the site that we're on. The difference here between the two is that the sand is left out of the porous pavement. So this is just stone and asphalt. And if you see here, you can see, I think Josh actually has another example here of a Rice Krispie treat.
A rice? Why do we call it Rice Krispies?
Well, just like a Rice Krispie treat is, the Rice Krispies and the marshmallow to stick it together. The porous pavement is built the same way, except that instead of the Rice Krispie pieces, you've got small stone and the asphalt binder to hold it together. So, people joke that it looks like a Rice Krispie treat, and it does, because it's built pretty much the same way.
Well, which came first, the Rice Krispie treat or the porous asphalt pavement?
I don't know, but the Rice Krispie tastes better.
Yeah, I bet. All right. So then there's a different kind of stone that goes into it.
Yeah, what we did out here at the site we're on is we filled up the basement with sand backfill, and once we got to within 3 feet of the top of the pavement, then we came in with larger pieces of stone, 1 to 3 inches. Here's a bunch of 1-inch pieces here. We actually used crushed concrete out here to try to recycle some material and save some money. We took the smaller stone here, you see, and we put it on top. And this allows the pavement, something to sit on. If I have the large open pieces, then the pavement will actually kind of drip through and get into the stone, which we wanted to avoid. So we come up with this smaller stone and kind of get ourselves still a porous system, but a tighter,
a little more solid base.
More solid base, exactly.
Right, but at the same time, as you said, it still has the holes between it, so the water.
You see the difference, yeah. The water will drain through this, but it will, it'll get stuck on this because of the fines in it. Concrete too. If you see, I got a concrete core, the same as the asphalt. It's solid, nothing's going through that. But we also have porous concrete. So similar to the porous asphalt, it's just stone and cement and water mixed together, and similar to what Josh was talking about, the Rice Krispie treat, it's real porous and the water drains through that too. So you have two different ways to do a porous system, either with the concrete or with the asphalt.
All right, great. I see that. All right. And let's see what happens if we try it right here on the pavement.
Okay.
All right. Pick your spot.
Well, I'm just going to bucket of water here. I'm going to dump it on the pavement and see what happens to it.
It goes through there like a sponge almost. It looks like it's really drawing it right down.
Yes, yes. Working exactly the way it's intended. Now that water goes through into the stone and into the subgrade. And like I said, you can see how it's almost like you can even see how it's filtered down through the pavements.
Okay, so this is the background. This is what we're all looking at. Now, I understand we got some demonstrations here. Josh, you doing the demonstrations for us?
Sure. We've got, well, this is a cross-section of what a regular pavement would look like. That's the mix over here on the top, and then the crushed limestone at the bottom.
Okay.
Over here, we've got the porous system set up. So you've got the porous asphalt on top, and then you've got the smaller stone up here, and the large stone down here. So you can see there's a lot of spaces for the water to get in there. And so we can actually pour water through this and show you how it works.
All right, now you're going to show me first what happens with the regular pavement and then the porous pavement? We'll move the Rice Krispie treat out of the way, I guess, here. All right, go ahead.
This might get a little messy here. So when rain hits the regular pavement, it has no place to go, and it can't drain through, and it just sits on top.
Right, I see the water is still sitting in the little tray here, and there really isn't any going anywhere. Okay. Right, and that was what we were talking about. When it runs off, it carries the pollutants with it, oil from cars or whatever's in there. Right? Now this is the new pavement, this is the porous pavement, and when we put the water in that, let's see what happens.
Okay, let's find out.
Well, I can tell you it's going right through. The tray is going to empty out, and I see it's draining out into the bucket right there, too. All right. Well,
If you look here, you see that there's water in the stone here. And when the site's a clay site, that's the idea, is that the stone holds all the excess water, and then that gets kind of filtered down and out the system. And we got a sample here of clay, so you can see that, water's really not going to get through the clay here. But then on a sand site like we have out on the site we're on, the water is going to get through that. So.
Ultimately, right, that water gets into that, then this goes into the natural water table and goes back into nature just like it was intended. Hey, thanks for joining us for another great episode of SciEngiMathePloration. We really learned a lot about civil engineering and what civil engineers do. I'd like to thank a few people, the Road Commission for Oakland County and our friend Craig Bryson, who sets these things up for us. And, of course, my new friends here at Soil and Materials Engineers, Josh and Jason. Thanks, guys, for showing me how this permeable pavement works. Be sure to check the credits for our websites and some other fun things you can do. Thanks for joining us. We'll see you next time.